This is Physics 2, Lab 4, Bar Magnets, and my name is Joshua Smith. Introduction. This lab is designed to familiarize students with magnetic fields and visualizing them. The purpose is to use physics principles and experimental data and observe, measure, and model how distance affects the magnetic field of a bar magnet. A little preview of the results right here. We have our n value, which is the slope of our plot that we'll show in a minute, and then the magnetic constant. And then the system is the bar magnet, and surroundings is everything else. Some fundamental physics principles here. We got I don't even know how to pronounce that, but this is very essential in calculating the magnetic field of a closed loop. And then at an infinitesimally small length. Then these two formulas right here model the distance dependence of magnetic field, because as you go outward, according to this equation, as you go outward, the magnetic field gets weaker. So we're gonna see if that's true. And then magnetic field created by a dipole. We are assuming that the bar magnet is a dipole, so this formula is very important in calculating field. The experiment, we slid the phone along the meter stick vertically and horizontally to find the approximate location of the magnometer, which is inside the phone, and we marked that location with tape. And then we recorded the magnetic field at multiple distance from the bar magnet, so along this, and then also a little off-axis action right here. Here are the initial conditions, which are like the distances and all that. Then our calculations are our average x component. And then down here, to get it more linear, we took the natural log, and this is what we got, and this is our best fit line. And then we use that to calculate our mu value right here, which we'll put into our computational model here in a second. Then also here the off-axis fields, distance, x component, measured, corrected, all that. And then some observations. The observations that we can confirm is when the magnometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and as the magnometer moves closer to the magnet, the measured component of the magnetic field increases. Here's a computational model. Here's our function for calculating the magnetic field, which is just using the last formula I talked about on the physics principle side of the dipole, magnetic field of the dipole. Then we altered the scale and distance to get the arrows looking good. Threw in some observation locations, perpendicular locations, and then we plotted those vectors. And then also did it for the off-axis one, which is this magenta one up here. But you can see the perpendicular arrows and the axis arrows, and they're looking about how we would expect them to. And here are the exact values and magnitudes down here. And then we can compare the magnitude of the off-axis field. We see it's a little bit different between the observational model and computational model, and this difference is likely due to these possible sources of error, such as surrounding electronics interfering with our measurements, rounding errors, errors due to like us looking at it and approximating, because the meter stick isn't perfect and our eyes aren't perfect. And then also we might have gotten the marked location of the magnometer a little bit wrong, and also errors due to assumptions. We assumed the bar magnet acted as a magnetic dipole, and we also assumed that external forces were negligible. Lab questions. What if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? Okay, so Earth's magnetic field would have altered our readings as we wouldn't be able to distinguish how much of the observed field was due to the Earth or due to the magnet, because it just collect those together. Because we would read the net magnetic field. Then what if you were to stick two identical magnets together end to end and run the experiment again? How would your measurements differ? How would you expect your measurements to differ? So the magnitude would have been 2 times the original, because the magnets are going in the same direction, north to south. But the magnetic field would, so yes, it would be double, but it would remain in the same direction because they're still going in the same direction. So that's the end of this lab. On to the next one. Spring break time.